In the second part of section 4.1, we are going to talk about a few subspaces that are related to linear transformations. The first one we're going to be talking about is what we call the kernel. The kernel of a linear transformation is defined to be the set of all vectors that linear transformation maps to zero. So this is actually very similar to what we were calling the null space. Remember, the null space of a matrix A was the collection of all, we'll go ahead and use V like we have in our definition up here. All the vectors V in, I guess, R in this case, where A times V is equal to the zero vector. This is exactly the same concept, but we're looking at it more generality. We're looking at any linear transformation. Basically, the null space is just a specific example of a much broader context. We'll look at some examples of computing the kernel of a linear transformation in a moment. But first, I also want to define the image. So this one's a little bit trickier because we can actually look at the image of various subspaces. So here we're looking at a linear map a linear map L from V to W, and S is any subspace of V. Then we can look at everything that was an S and look at what happens to it when we put it through L. So if V is an S, we take its image, what we get out from plugging V into L, and we put it into this space. And we call that the image of the subspace S in the linear map L. If we take the entire vector space V as a subspace, every vector space is a subspace of itself, but we can take the image of the entire vector space and we just call that the range of L. It's every vector in W that we can get out of this function. And it turns out the kernel of any linear transformation is always a subspace of our domain. So here we have our L going from V to W. The kernel is a subspace of V. The image of any subspace, so if we take any subspace S of V, the image of that subspace is always a subspace of W. And those are consequences of the fact that this is a linear map. If this was just any arbitrary function, this would not be true. But as long as we're dealing with a linear map, then this kernel is always a subspace, and the image is always a subspace. So it just means that the range is always a subspace. And kind of going back to range, we can do the same thing that we did with, if we're looking at a matrix A and asking, well, what B's can we get out of this? Because that's what the image is really doing. We can basically see that for L of x equals A of x, A times x, the image of Rn in this case is just going to be the column space of A. So kind of going back to what we were talking about in the last section. These are, again, broader context. We can actually talk about kernel and image in the context of, say, linear functions between the collection of continuous maps to continuous maps on a closed interval, anything like that. So these are very general ideas, but we already see that they are just generalizing what we're already familiar with, what we've already worked with. So let's look at a couple of examples of this. So let's take a linear map. So let's just take one of the ones that we worked with before. So one of our first examples of a linear map from R2 to R2 was L of xy is equal to x0. What would be the kernel of this map? We're asking what things get sent to 0. If we want this to equal 0, 0 when we come out, what does that say about x and y? Well, L of xy, again, from our definition, this is just x0, and we want x0 to then be the 0 vector. What does that say about the x and the y that we had to put in here? Well, it doesn't say anything about y. Y is no longer part of our equation, but it does mean that x has to equal 0. So that means we can take our kernel to just be the set of all vectors x, y, but really just 0, y, because we need that x to be 0, and we can let y be whatever we want it to be. So y here is any real number. That is the kernel of L. What about the image of L? Or let's just look at the range. We'll find out what the range of L is. What vectors can we get out? Well, normally that's kind of a tricky question. It's still a tricky question from back when we were talking about ranges of functions in the first place. We always would be able to talk about domain pretty easily, but range was always kind of a pain. It's going to be kind of the same here until we actually do talk about some stuff in 4.2. Then we'll find that we can use some of the stuff that we've talked about in the last chapter in order to help us solve this question. But for this particular example, it's not too bad. We're allowed to pick whatever we want for x. So the x here can be whatever we want it to be. But the second part of this is always going to be 0 no matter what, just from our definition. So it's not too hard to see that L of R2, the range of L, is just going to be the set of all vectors x0, where x can be whatever we want it to be. It can be any real number. That is our kernel and our range for this particular function, for this linear map. And note that those are both one-dimensional subspaces of R2. What about something like L of xy is equal to yx? So here we don't have something immediately going to 0. In fact, both of our variables survive. We want to ask, what is the kernel of this thing? So we're asking, actually, we don't even have to write this on another line. If we set this equal to 0, 0, if we say that x, we want to look at what x and y actually end up with 0, 0 at the end. What does that say about x and y in the middle? Well, in this particular case, well, y has to equal 0, and x has to equal 0. So in fact, the kernel of this map is just the vector 0, 0. That's all that's in the kernel. Now, we do have to have that in the kernel. We always have the 0 vector in the kernel. In fact, we could just write this saying that we're talking about the 0 vector. But the 0 vector always maps to 0. We know that to always be true. But it's really the question of what else could be there. In this particular case, there's nothing else there. It only 0 maps to 0. What about the range of this function? What is L of R2? Well, we can ask ourselves, what possible vectors can we get out of this? if we want a particular vector, well, we just pick y and x to make that work. So if we want the vector 3, 1, we want this y to equal 3 and this x to equal 1. That means we'd have to plug in the vector 1, 3 to begin with. But we can do that. And it doesn't matter which vector in R2 that we pick, we can always manage to do that. So we can actually get any vector out. The range of this linear map is all of R2. We can actually get everything in R2. So we have an example where the kernel is a zero-dimensional subspace. It only has the zero vector in it, but the range is a two-dimensional subspace. And if you remember some stuff from the last section, maybe you can kind of see that there's sort of a duality to this. That the dimension of the kernel and the dimension of the range are not actually separate. There is a connection between those. But we will get into that a little bit later. Let's see here. Let's do a little bit more of an interesting example. Let's look at our map that we talked about before from R3 to R2. So let me just put over here that this is going from R3 to R2. So we start with x, y, z, but we're mapping to x plus y and z. And we want to ask, what is the kernel of this map? What is the range of this map? Well, what happens if we set this thing equal to 0? So we want, in essence, that x plus y comma z to be the 0 vector, that we get 0, 0 out. Well, of course, in this case, that means that the z had to have been 0 in the first place. But x and y don't have to be. This actually corresponds to the equation x plus y equals 0. So these are the two equations we have. That means if we pick a value for x, we can find out a value for y that works for it. In other words, we can solve for y and get that y equals negative x. There's nothing really too much more we can do with that. So we'll just go ahead and turn this into our kernel. Our kernel is a set of all vectors where we can pick whatever we want for x, but that forces y to be the negative of that. And then z always has to be the 0 vector. So here, again, x can be any real number we want it to be. And that's our kernel. Now you can ask, what is the dimension of that space? And what you can kind of see here is that everything is actually a multiple. Every vector in there is a multiple of the vector 1, negative 1, 0. So we just basically take x times this vector, and we get whatever vector in here. So actually this is a one-dimensional subspace of R3. What is the range? Well, again, range is a trickier concept. We actually have to think about that a little bit more. But we can actually just realize that if we want to have, so if we want the vector, say, x, y, to come out of our linear map, then all we need to do is say plug in x, 0, y. That's going to give us x plus 0, comma y. But x plus 0, of course, is just x, y. So if we start with any vector in R2, there is something that will go to it. So actually, the image, or the range of this map is actually all of R2. Everything is part of the range of this. Finally, let's go ahead and look at our differentiation and integration linear maps. So remember so this is going from from C1 of AB to C, but we're taking a function f and we're getting its derivative out from here. And we want to ask, what is the kernel of this map? In fact, we might not even call this L. Let's call this D. D for derivative. That's a pretty commonly used letter for this particular linear map. So what is the kernel of D? Well, we're just asking what functions have derivative equals 0. When is f prime equal to 0? Well, that only happens if we have a constant function. If a function is constant, its derivative will be 0, and the only time a function's derivative is 0 is if it is constant. So the kernel of the derivative operator is the collection of all constant functions. What about the range? So taking the entirety of differentiable functions on AB, and we're asking, well, what are the possibilities here? What possible functions can be the result of differentiating a function? Well, if we do have a function to begin with, can we find a function whose derivative is equal to that function? So we start with f. Is there a g where g prime is equal to f? Is that a possibility? Well, we can just integrate. So g is just going to be the integral of f, and we don't even really have to, we can write this as just an indefinite integral, or we could try to do some trick like we did with the fundamental theorem of calculus. But we can always integrate any continuous function, and so we can, and that integral will turn out to be a differentiable function. So in fact, yes, we can. Every function that is continuous is the derivative of some other function. And so this is an example where the range is everything. What about integration? So now we're going to take our function. So now we're just dealing with continuous functions going into our linear function. But we're getting real numbers out. And we're asking, what is the kernel of this map? This is a linear function on functions. Kind of a weird thing to do, but that's what we do. And we're asking, when is this equal to 0? When does that equal 0? Well, that's actually a tricky question. If we're looking at something like, I don't know, f of x being the sine function, and maybe we're going from negative pi over 2 to pi over 2. Maybe that's our a and b. Then we know this is actually equal to 0. We can actually work out what this is. So there's actually a lot of functions that map to 0 under this linear map. So the kernel of L has a lot of stuff in it. In fact, that's the trickier question in this case. The image, the range of this function, is in fact a lot simpler. We're asking what possible results can we get from doing an integration of a function on the interval from a to b? Well, whatever result we get, we can always multiply that result by a number. We can actually get any real number out from doing some sort of integration. So this is a rare situation where the kernel is a lot harder to figure out than the range. But it's kind of fun to think about it. To think about what the possibilities are for the kernel for this function. All right. Well, there are more examples, and you can kind of take a look at some of them and try to think about how you would compute the kernel and the range. But we will actually see some ways of coming back to that question, maybe answering those questions a lot easier, or at least in a way that we've already looked at before. So we'll gain a lot of information in the next section, in 4.2. This will be a very important section for us to be able to do anything with these linear functions. So see you guys in the next class.